I will introduce Chapter 6, which will talk about capacitors and inductors. So this chapter has two new components that we're going to talk about. I'm going to split these lecture slides into two halves. The first half we'll talk about capacitors, and the second half we will talk about inductors. And so this is a little bit different than what we've been talking about before, because now, as you're going to see in this chapter, some differential equations will start to appear. So now our analysis will require us not only to just use basic algebra and solving simultaneous linear equations, we will now need to solve some first order or second order differential equations. And more of those will appear in chapters 7 and 8. But it is important to note that in resistors, though, the resistors that we've been talking about really just dissipate energy. So what's actually happening is, as electrons are flowing through these resistors, they are actually dissipating energy in the form of heat. So the resistive material that's inside of resistors, usually some kind of a carbon film, is actually just slowing down the flow of electrons, and in turn there is some frictional loss in there, and that is leading us to dissipate energy in the form of heat. Capacitors and inductors do not dissipate energy. Capacitors will actually store energy between two plates in the form of stored charge, storing up voltage, and inductors will actually store energy in the form of electromagnetic fields. And so more about that later. We're going to learn how to analyze these components inside of a circuit, and we'll really start to get into the mathematics of that in the next chapter. So continue on in this video and we'll start talking about the capacitor. So here is a model of a capacitor. Generally, you can think about a capacitor as being a passive element constructed from two parallel plates. And so they may be parallel plates just straight across from each other like this. Inside of some capacitors, it may be parallel plates that are wrapped around and stuffed inside of a cylinder. You may see them as round, you may see them as square. They come in a variety of different shapes, colors, sizes, but they all are capacitive in one way or another. Some have polarity and some do not, meaning you have to put them in your circuit in a particular orientation with the positive and the negative oriented properly, or you will have some problems. But typically what you have are two plates that are made out of conductive materials, a lot of times aluminum or something like that, and then there's something between them. In some cases it could just be an air gap. In other cases it might be a sheet of paper or cardboard. You might see some ceramic discs put in there, mica, all sorts of materials. And in some cases you might even see some kind of dielectric paste. And so depending upon what's inside, that gets you into the permittivity of the dielectric, and that's given by the Greek letter epsilon. Our surface area of each of these plates is given by A, and then the gap spacing is given by a distance D. And so if we're trying to calculate capacitance, we see that capacitance is directly proportional to our permittivity of the dielectric material, directly proportional to the area of the plates, and inversely proportional to the distance between those plates. So the further those plates go away from each other, the lower the capacitance. The bigger the area of those plates, the more the capacitance. And then, of course, depending upon what is between them, whether it happens to be a dielectric paste or cardboard or ceramic, you're going to see different permittivity in the film. And so that is going to be given in terms of farads per meter in there. The unit of farads is 1 coulomb per volt. So that gets into this idea of how much charge can be stored for every volt that is across the capacitor. So if you have more coulombs per volt, then that means for any given potential you could store more charge. That means more electrons are going to be across that capacitor. 1 farad is really quite a large amount of capacitance. Typically the capacitors we're going to be using in lab that you might see in a lot of your microelectronics, maybe on the order of picofarads or microfarads. You may see some nanofarads, but they are typically a much smaller unit than just a single farad. So just like in resistors, we oftentimes see kiloohms, and so it's not just an ohm. 1 ohm is actually a very small resistance. Typically we might see kiloohms or maybe even mega ohms. In capacitors, it's the exact opposite. Capacitors tend to be a very small number of farads, pico being on the order of 10 to the negative 12, micro on the order of 10 to the negative 6. Nano, of course, in between there at 10 to the negative 9. So, with different types of capacitors, they are often, as I mentioned, rolled up before being housed inside of a metal or plastic film that surrounds them. They can have different materials, polyester, polystyrene, mica on them. The electrolytic capacitors are the ones that are polarized. And so typically electrolytic capacitors will have one side that will very clearly indicate the negative side, so that'll show you exactly how it should be put in a circuit. If you're talking about just simple ceramic disc capacitors and other things like that, they can go in either way, and there's not a set polarity to them. You can also have trim capacitors or variable capacitors, and that can actually be used as a sensor. One of the labs that most sections of the 3050 class, which is your sensors, measurements, and controls class, will get into, is using a variable capacitor as a proximity sensor or a distance sensor. And so based upon the displacement of two parallel plates in a capacitive sensor, you can actually detect how far apart the plates are based upon a signal response in a circuit that involves that variable capacitor. So in this case, if you see an arrow across the capacitor like that, that is a trimmer capacitor, that is a variable capacitance. And so in this case, we're going to have a positive voltage here, current flowing this way, and your capacitance C. So here are just some of the different shapes that you might see for capacitors. As I mentioned, some of them are round, so in this case you've got some round plates, and this might have some kind of a polyester or plastic coating on it. This one is a little bit shinier, more rectangular plates. Here you have an electrolytic capacitor, and this has a polarity to it, and in this case you have leads coming out one side or the other. There are also electrolytic capacitors that have both leads coming out of one side, and there's a variety of uses for capacitors. In some cases you may want to block out a DC signal, so maybe you've got an offset voltage and you're really just interested in the sinusoidal nature of a particular signal. You can use capacitors to eliminate some of the DC signal and keep the AC. You might also be interested in shifting the phase, and so there is a phase shift that happens when you have a capacitive load. You might also want to store some energy. So for example, in old cameras that had flash modules in them, one of the ways that you would be ready to take flash pictures is you would actually store up charge on a capacitor, and then when it was time to take that flash photo, the capacitor would actually release the charge into the flash module. If you've ever heard a camera where you hear this little high-pitched frequency as that it's charging up, getting ready to take flash photography, what's actually happening is it's charging a capacitor and it's storing that energy. Why is it doing that? Well, the battery itself, typically a AA or AAA battery in a camera, doesn't have enough current sourcing capability to be able to use the flash module with it. And so what happens is you actually store the energy in a capacitor, and then the capacitor can discharge that charge very quickly through the flash module, much faster than the battery is capable of doing. You might also want to suppress some noise. So perhaps you have a noisy power supply or something like this. You have some extra ripple currents on top of things, or just some noise in a particular signal. A capacitor can actually help to smooth that out. You can use capacitors to filter, so you can create low-pass filters, which would allow low frequencies to pass through. You can create high-pass filters, which allow high frequencies to pass through, or band-pass filters that allow specific frequencies to pass through. So a typical example of a band-pass filter is something like an FM or AM radio. In the tuning of that radio, you're expressing a particular frequency that you want to listen to. So let's say you like radio station 93.3. That's 93.3 megahertz is the broadcast signal, and typically radio stations are no closer together in any given area than 0.2 megahertz. And so what you'll actually do with your radio is create a band pass filter that would allow any frequency up to, say, 93.4 down to 93.2 to be able to pass through, and you would filter out all other signals. So that way, if you want to listen to the music or the broadcast on that particular frequency, then you keep that one, allow that to pass through, and then any other frequency bands you want to block out. So that way, you're getting your radio station and you're not getting all the other radio stations or all the other signals. You can also use capacitors to start motors. Very similarly, if you're trying to run something and you can't source enough current from your power supply, your capacitor can actually store that charge so you can get enough current to actually start a motor running. Capacitors, when the capacitor is connected to a voltage source, what actually happens? Well, you've got a difference in potential across them, and the capacitor will actually gradually start to build up charge. It's going to have positive charge on one plate and negative charge on the other. And so gradually the potential across that capacitor will increase until it gets to the voltage source that's there. It might be in terms of a voltage divider, so you may have it divided with some other components, but it's going to keep charging. And once it is fully charged, it's going to behave as an open circuit, so no more current will flow, no more charge can come in. And eventually the charges will be equal in magnitude across the two plates, and you can see that the amount of charge is going to be directly proportional to the capacitance of the capacitor and the voltage across them. And so you can also figure out, based upon taking the first derivative, what the relationship is between current and voltage. So if you remember, current is charge over time. How much charge is passing in any given time? So I is really equal to dq dt, where that is the change in charge with respect to the change in time. So if we take this equation and we take a derivative of both sides with respect to t, where charge could be changing with respect to time, voltage could be changing with respect to time, and your capacitance is a constant, what you get is dq dt, better known as I, or the current, is going to equal C, that's a constant there, times dV dt. So this is one of the most important equations you're going to remember whenever you're going to be analyzing any circuit that has a capacitor. I equals C dV dt. So this is a first order differential equation that expresses the relationship between current and voltage. And in order for that to work, we are using the passive sign convention, which means that your current flowing into the capacitor will hit the plus on that top side and then the minus on the back side. So that is our passive sign convention. So stored charge, if you take this particular equation here and just integrate both sides, what you end up with is the voltage current relationship. If you want to find voltage, it's 1 over C, the integral from some initial time up to the current time of I, and in this case, so we're not confused with the current time versus the function of time, we'll just say I of tau d tau plus some initial. So what the initial value means is we have some memory. So capacitors ideally will actually store charge until the end of time. So if we have an ideal capacitor, we put some charge on it, and then we just disconnect it from a circuit and put it on a shelf, ideally it would hold that charge forever. So that is an important thing to note. If you have a circuit with any capacitors in them and you cut power to it, that capacitor could very well still be holding on to some charge. And so you need to wait a certain amount of time just to make sure that charge is discharged before you start working, or you may find yourself shocked by this capacitor. A real capacitor actually has a parallel resistance. We'll talk about that in just a moment. So capacitors in the real world will eventually discharge if just left to their own devices, but an ideal capacitor will store that charge forever. The instantaneous power delivered here, P equals VI, and so if we remember I equals C dV dt, and then we've just got V times that, the power delivered to the capacitor at any given time is CV dV dt. And the energy stored in the capacitor is given by omega equals 1/2 CV squared. So some properties of the capacitor. These are very important to note when you're analyzing circuits, and this will tell us what's going to happen as certain conditions change. When we get into analyzing some problems in Chapter 7, we're going to rely heavily on these two properties. When the voltage is not changing, the current through the capacitor is zero, meaning you can think of that capacitor as being an open circuit. So if you're not charging up the capacitor, if the capacitor is already fully charged to where, let's say you have a voltage source and the capacitor has the same voltage at this point as the voltage source, it's now going to behave like an open circuit. Also, the voltage on the capacitor's plates cannot change instantaneously. So you might have a voltage source that you turn on and off, but the capacitor cannot instantly jump from one voltage to another. So if you have no volts across a capacitor, you can't just turn on a 5-volt supply and then all of a sudden there's 5 volts across the capacitor. It will ramp up and it will ramp down. We will see that illustrated in a lab in a few weeks. Once you guys are done with your temperature alarm design project, we will actually see charging and discharging capacitors, and you'll see that it does take a little bit of time for that current to flow in and the charge to ramp up. You cannot instantaneously change that. If you go back to the differential equations that govern this, if you were to instantaneously or have a stepwise change in the voltage, what is the derivative of a stepwise change? Well, it goes to infinity, and what that would mean is in this relationship, your current would therefore go to infinity. And so infinity is generally not a good thing for any real-world electronic component. You don't want infinity current, you don't want infinity power, and you just can't get it. And so what that's going to do is that will cause some problems if you try to instantaneously change it. So usually what you'll see in conjunction with a capacitor is a resistor, and that will allow that current to trickle into the capacitor over time and eventually charge it up, rather than just instantly having a change in the capacitor's voltage. So if the voltage on the capacitor does not equal the applied voltage, charge flows in, and then if you start turning off the applied voltage, then charge will start to trickle back out. An ideal capacitor doesn't dissipate energy, it just stays there and can be retrieved later. And a real capacitor actually does have a small resistance in parallel with the capacitor, so that will actually discharge the current over time, discharge the stored charge. The resistance is typically pretty high, so it's 100 mega ohms there. Sorry, I misspoke. I said it was small. It's actually a quite large. It's nearly like an open circuit, but it is a real and finite resistance, so there will be some discharging. Now, let's talk about what happens if you combine capacitors in parallel. Well, if we had a current source and we just had several capacitors, let's say N capacitors lined up in parallel like this, you might want to ask yourself, well, what would be the equivalent capacitance to all of these parallel capacitors? How could we rewrite this? Well, if we go back to the principles that we already know, we know any components that are in parallel happen to have the same voltage drop across them. What that means is the voltage changes across them are going to be at the same time. So if you change the voltage across capacitor 1, you're also going to change the voltage at the same rate across all of the capacitors in parallel. And we also know from Kirchhoffs current law, whatever the current of this source is, that has to equal the sum of all of these branch currents. And so I is going to equal I1 plus I2 plus I3 all the way up through the current through the nth capacitor. And so if we go back to that differential equation, what does that mean? I equals C1 dV dt plus C2 dV dt plus C3 dV dt. All of these dV dt's are the same because we're talking about components in parallel, and as the voltage changes, it changes at the same rate. And so you can rewrite this as the sum of the capacitors, capacitance, times dV dt. And so that turns out to be the equivalent capacitance. So here, when you have capacitors in parallel, they can add. Just the opposite of what we saw in resistors. So capacitors in parallel can just be added together, just as resistors in series could be added together. So now you might ask yourself, well, what can we do with capacitors in series? Well, here, now let's say we have this voltage source and we've got the same current flowing through because now all of these elements are lined up in series. Let's see what we could do to add up those currents or add up all the capacitors in series. Well, if we apply Kirchhoffs Voltage Law, we know that the voltage of this source is going to equal the voltage dropped across all of those capacitors. And if we go back to our integral relationship here, we see that the voltage across the first capacitor is 1 over C1 integral of I of tau d tau from T naught to T plus the initial condition there. Here we have the same integral, but it's 1 over C2 plus the initial voltage there, all the way on through. And so now what we could do is condense all of our initial voltages into just this V T naught. So that's going to be your V1 at T naught, V2 at T naught, all of those initial conditions we'll just add together. You notice that because everything is in series, the current is exactly the same. So the integral itself is exactly the same. As the current changes in one, the current must change in everything that is in series. And so in this case we condense that, and we really just get 1 over C1 plus 1 over C2 plus 1 over C3 all the way up through 1 over Cn. So it's the sum of the reciprocals plus the initial condition of voltages on all of them. And so we can write that as 1 over the equivalent capacitance in there. And so you have the same reciprocal relationship as we had for resistors in parallel. So capacitors in series add just like resistors in parallel do with this reciprocal relationship here. Alright, so that's how we can combine some series capacitors. So another way to think about the combinations, when you combine capacitors in parallel, what you're really doing is increasing the surface area of those plates. If you just line them up together, and put one right next to the other, you could think about that just adding the area of the plates on either side. That would increase the overall capacitance. In terms of what's happening when you're putting things in series, you're actually just separating the plates a little further down. So if you think about that as one big capacitor, you have a capacitor next to another one, next to another one, and if you just look at the two end plates, those are further apart than just one individual capacitor. So that talks about all we're going to talk about with capacitors, and in the next video we're going to talk about the inductor.